Okay. Okay. I think that's all I do before I start. Oh, maybe I should change that. Uh, nice. Okay. Oh. Okay. Okay, I think we can start. So hello everyone. Welcome back to the Company 30 tutorials. So today we'll be working through a few of the problems from problem set 5. In particular, we're going to be talking about exercises related to Turing machines, which I believe you've covered. So in particular, we're going to be looking at Turing machines from two different sort of perspectives, and that's going to be reflected in the exercises that we're going to solve. You can see Turing machines as just any other automata that we've sort of seen in class, so as a language recognizer. So we're going to do exercises where, given some language, we want to design a Turing machine that accepts that language. But we're also going to look at this other cool property of Turing machines, which is that they can be used to implement functions. And so there's also some exercises in the problem set related to this. So we're going to do a bit of both. Maybe before we start with the exercises from the problem set, though, just to get people warmed up a little bit, given this cold November weather, I'd like to do a quick warm-up review of Turing machines. And to do that, we'll look at an example of a Turing machine where we want to know what strings are accepted by the following deterministic. So what type of Turing machine in particular? It's going to be the deterministic infinite tape Turing machine that you're sort of hopefully already familiar with. That's been sort of described in the lecture a few times. So what is M going to look like? It's going to be a 4-state Turing machine with an accept state, a transition to this other state Q1, and transition back to Q1 like this. Okay, so this is the Turing machine, and we want to determine what strings are accepted by it. So, hello. Thank you. Maybe before we look at the solution, so the way to sort of approach the solution to this question, I'd like to maybe review the fundamental properties of Turing machines, because they're a bit different from the FAs and the PDAs that we've seen so far. So one thing that you can sort of notice almost immediately is that the transitions look a bit different from the things that we've been looking at so far. In particular, this is the syntax that I'm using. So I have some letter, then an arrow, and then some letter, and then either left or right. So what this syntax essentially represents is, I have, like in previous machines, I have a tape, right? And I have a pointer that reads individual letters from the tape. So the X on the right here is the letter being read. But now not only can I read letters, I can also write letters to the tape. So the Y here is the letter being written to the tape, right? And the other thing that's nice about Turing machines is, for FAs and PDAs, you would see what's on the input tape, do something, and move the pointer to the right. You can still do that. That's what the R stands for. but now you can also move the pointer to the left, right? So this tells you the direction of the pointer. Okay, so for instance, if I'm at state Q1 and the transition from Q1 to Q2 tells me if I read an A, write an X, and move left, then the way that I get from Q1 to Q2 is I read this A, I overwrite it with an X, and I move my pointer to my left. So the pointer is now here. It's maybe pointing at a blank. This is the symbol I'm going to use for a blank. So symbol for the blank is an empty square. I'm not using B because that's a bit confusing since we've been seeing alphabets with A and B. So the blank is just going to be this empty square for our purposes. And instead of being at Q1 here, because I'm sort of changing state, I'm going to be at Q2. Okay, so that's kind of what's going on here. Now, the other thing that I want to talk about maybe before I sort of talk about the potential or the solution to this question is how do Turing machines accept, right? Because it's a bit different than the previous machines we've looked at. So convention for acceptance. Essentially, the way that Turing machines accept is kind of like a return statement in a Python or Java program. As soon as you hit it, you sort of accept. And it doesn't matter if you have stuff left to read. If you hit an accept state, then you've accepted the input string, right? So the convention is once your Turing machine reaches an accept state QA, the Turing machine halts and accepts. Okay, so this is very different from FAs and PDAs. In FAs and PDAs, if you got, remember if I was reading maybe A, B, B, and reading B, I got to the accept state here, right? Then this isn't an accept in an FA, right? So not in an FA or a PDA, because in both of these FAs and PDAs, I have to read the entire string. So just because I was able to transition to an accept state, if I don't have a transition here, I just halt and I jam and I reject, right? So this is very different in Turing machines, right? In Turing machines, if it's the sort of same situation, you're reading a B from this state, maybe you don't touch it and you move your pointer right, doesn't really matter, and you hit an accept state, this is an accept, right? So this is very different, right? It's this is an accept for Turing machines, right? So this is definitely very different, and it's something to consider when you're thinking of the answer. Well, we'll see in a second why this is kind of important. The other thing that I maybe want to mention also before I talk about the solution to this question is in Turing machines, when you don't accept, it doesn't necessarily mean that you reject, right? So in Turing machines, not accepting does not mean rejecting. Okay, so what do I mean by that? In Turing machines, not only can you reject, you can also loop, right? And looping is not the same thing as rejecting, right? So rejecting in Turing machines, is essentially the Turing machine ends up in a state where no transitions can be used to continue its computation. and the state is not an accept state. So a Turing machine ends up in a state which is not an accept state, where no transitions can be used to continue its computation. So for instance, if my tape is pointing at B, and I'm in, let's say, state Q3, and the only transition I have is for A, right? Maybe this transition goes to the accept state, but if I'm at Q3 and I'm reading a B, I don't have a rule for the B, right? And so that means that my Turing machine jams or halts, and it's halting or jamming not in accept state, so that means it rejects, right? So the Turing machine halts in a non-accept state, which means that it rejects, right? So on the other hand, there's also the possibility that the Turing machine loops, right? And so looping in Turing machines is essentially when the Turing machine never halts, right? So when the Turing machine never halts, right? So what does this kind of look like? Imagine that I have a blank and then A and a pointer, and maybe I'm at Q2. So from Q2, if I read an A, maybe I write the same thing. So I read an A, I move my pointer left. Then from Q3, if I read a blank, I don't touch it and I move right. And suppose like there's nothing else that can really help me here, then what's going to happen is I'm at Q2, I read an A, I move left. Then I'm at Q3, I'm reading a blank, I move right. And then I move left, and then I move right, and then I move left, and then I move right, and this never ends, right? So I'm in an infinite loop, right? And an infinite loop, so here, the Turing machine loops forever. And an infinite loop, very importantly, is not the same as rejecting, right? Rejecting is a decision, right? If I reject a string, that means that I've come to the conclusion that I should reject it. Looping is you're waiting forever for the answer, right? So this is not the same as rejecting. Okay, so hopefully that makes sense. Hopefully this is an acceptable review, which does not contradict anything that you've seen in the, maybe it is.
For the accepting states?
Yes, so what I'm going to be assuming, so my assumption, which is a safe assumption, is there is no transitions from the accept state, right? So this is why when you reach the accept state, you accept and that's it, you're done. Yeah. Thanks for the question. Cool. Okay. So now, to be honest, maybe I should have just started with the review and then given you the question. So, because now I essentially just have to copy it. So let's do that. Okay, I'm just gonna let people finish writing. Oh, paste image. Oh well, not exactly what I wanted, but okay. So remember the question was now given all this mumbo jumbo about Turing machines and whatever, how they accept and reject and loop, what are the strings that are accepted for this particular Turing machine? So if I look at this Turing machine, I see that there's a transition for A and there's a transition for B. So let me maybe analyze this in a way that I kind of already know will be, yes. Can I make it bigger? Yes, absolutely. Thank you for the, it's of course big enough for my iPad, but not enough for you. Makes sense. Okay, nice. So what I'm going to do in this analysis is, I see that from Q0, when I read an A, I can go to QA. When I read a B, I go to Q1, and then there's some behavior. So I'm essentially that's how I'm going to sort of split my analysis. I'm going to say, well, let's start by analyzing, so analysis. The first case is strings starting with A. Right, so if I have a string that starts with A, maybe A, B, A, what's going to happen, right? Well, my Turing machine takes this input string, it places it on the tape to the left and to the right because it's an infinite tape. There's an infinite number of blanks, which I will not represent because that would take infinite time. And I start at Q0, so the leftmost part of my string. And what do I do? Well, what does the Turing machine tell me to do? It tells me if I'm at Q0 and I read an A, then I go to QA, right? But remember what we just talked about. If I go to QA, I'm done, I accept, right? So that means that regardless of what was here, right, I would, my Turing machine would see this, this A at Q0, and it would transition to this QA, regardless of what this was, what this is or was, or will be, it will accept, right? So no matter what comes after the starting A, M goes to QA, and so therefore accepts, right? So that means that I at least know that a subset of L of M, where L of M represents the strings accepted by M. So a subset of this, because I have to analyze the other strings, a subset of this is all of the strings that start with A. So this regular expression, right? Okay. So hopefully we're convinced by this, right? As long as my string starts with A, then I accept it. What happens if my string starts with B? So for instance, I have the string B, A, B. Well, I have the string B, A, B. Let's look at the Turing. It's not big enough. Can I paste it again here? Yes, exactly what I wanted. Okay, let's see if this works. Okay. So if I'm starting with a B instead, and I'm at Q0, let's see what's going to happen. Let's get rid of this text. It's kind of annoying. So I'm at Q0. I'm reading a B. So that tells me that I should move my pointer right and be at Q1, right? I'm at Q1 and I'm reading an A. So if I'm reading an A, then this tells me that I should write an A and move my pointer back left. So my pointer is back left. I'm at Q2. Right now I'm at Q2. Now I'm reading a B, right? So I'm reading a B. I move my pointer back to the right, and I'm at Q1, right? And I'm at the same place where I was 2 moves ago, right? And because this is a deterministic Turing machine, exactly the same behavior is going to happen. So I'm at Q1, I'm going to move my pointer left, then I'm going to move it back right. So I have a loop, right? And so it doesn't matter actually what was after this B, right? If it was another B, I would have moved back left. There was a B here because I transitioned like this, so I'll move back right. So regardless of what is after the B, I'm going to loop on it, right? So it turns out that a string starting with B, they cause M to loop forever, right? So this is not a set that is a set of strings that is accepted by the Turing machine, but it's also not a set that is rejected by the Turing machine. In fact, there's only one string that this Turing machine rejects. What string might this be? Yeah? The empty string, yes, very good, right? Why is the empty string a string that gets rejected? Well, the third case is the input string is the empty string. Let's just assume I have some reference blank where Q0 starts. Well, I'm at Q0. My machine starts at Q0. It has no transitions for the blank. The convention is it halts. It's not halting in QA. It's halting in Q0. That's not an accept state, so it rejects, right? So that tells me that M rejects the empty string, right? So if we want to tie this analysis all together, L of M is all of the strings that start with A. The strings that cause M to loop are the strings which start with B. And then the strings rejected by M is just a set that contains the empty string. Okay, nice. All right, yes, question.
So when you say that the Turing machine calls, it's not that there's no transition function on that state, but no transition function for the given input.
Yeah, that's right. I was maybe a bit ambiguous. When I say the Turing machine halts, that means that at that given state, in that given configuration, the Turing machine doesn't have a rule for that configuration. It doesn't know what to do, and so it halts. Right. Yes?
Can I see the diagram again, please?
Yes, you can.
If you were to remove the T transition from Q1 to Q2, then B would also be rejected, right?
Let me think. Yes. Yes. Cool. Any other questions? Yeah.
Would you like mostly analyze this with like graph, like as a graph to see like what leads to the accepting states, like deduce what are the what's set element?
Yeah. In practice, like if you're given like the general strategy for solving a question like this is first of all, look for how you get to QA. If there are many QAs, then look for how you get to any of the QAs. That tells you what gets accepted. That doesn't tell you, though, if everything else gets rejected or looped. So then you have to be a bit more careful to check for infinite loops. Yeah. Nice. Good question. Any other questions? No, we're good. Okay, cool. Okay, excellent. So now that we're warmed up, let's move on to something maybe a bit more interesting. A question from set 5. So this is going to be question 1A, which arguably will also be a bit of a warm-up, where we want to design a deterministic infinite tape. So that's what this acronym stands for, deterministic infinite tape, Turing machine for the language A star, B star, right? So when I say for, I mean that accepts all the strings in A star, B star, and only all the strings in A star, B star. Okay, so this is deterministic infinite tape. Probably not surprising that we should be able to do this because A star, B star is regular, right? So if I can create a DFA for it, then, hopefully I should be able to create a Turing machine for it because we've been talking about Turing machines being the most expressive model of computation. So it would be a bit embarrassing if we couldn't do A star, B star. Okay, so how are we going to do this? The way that I like to approach designing Turing machine questions is I always like to think of what my tape will have and how I will sort of reason about the pointer and the moves on my tape, right? In this case, it's kind of nice because I don't even have to really mark anything, right? So my pointer is going to start at this first A. I'm going to tell my machine, well, loop through these A's, right? Then at some point, you're going to hit a B. And at that point, you want to loop through all the B's. And you sort of go to the accept state if and only if at some point you see a blank. And there's no possibility of having like some extra strings here because we're assuming that the input alphabet is AB and the blank is part of the sort of tape alphabet. So it's not in Sigma. Okay, that's going to be the general idea. So not all that much different from what you would do in an NFA or a DFA. So let's try that. From Q0, I'm going to loop through the A's, right? Then at some point, I'm going to see a B. That's going to allow me to, or cause me to transition to Q1. At Q1, I'm going to loop through the B's. Notice that for all of these transitions, I'm using right moves. Makes sense because I'm kind of just trying to replicate what an FA would do, and an FA always moves right. Then at some point, I should hit a blank. In fact, I must if the string looks like A star B star because I don't have infinite strings, right? At that point, I'll move again right. Doesn't matter at this point. I can move right or left, and I'll hit the accept state and accept the string. So there's a bit of a problem with this machine. In fact, it's missing a case. Yes. What is the case? Yes, right. This cannot accept the empty string, right? Very good. Excellent. So it's missing a few cases, right? It's definitely going to accept a string that looks like A's and B's, right? That's cool. It's also definitely going to accept a string that's just B's, right? Because, it'll transition once, then it'll go through this, and then it'll hit the blank. The problem is if it just has A's or if it's the empty string, right? So what's a possible fix for this? Question for you? Yeah. Yes, very good. The one thing though is when we say empty state transition, we don't mean something like this, right? We mean very good. Just to be clear, there are no epsilon transitions in Turing machines. In fact, in deterministic Turing machines, that you can use them in non-deterministic Turing machines. So a blank transition is all you kind of need, right? So this is going to work because if the string is just empty, then blank, blank, accept. If the string is just A's, then go through all the A's, blank, blank, accept. Nice, nice. Thank you for the fix. Cool. Make sense? Yeah.
There's some ambiguity, right? Because you can.
There's some ambiguity.
Yeah.
I don't see any ambiguity, but.
What's the point?
What's the transition? The point of having this structure is to ensure that you have A's and then B's, right? You definitely don't want to have the same transition for A and B here, because then you could have A, B.
B goes to B.
B goes to B here?
Yeah. Why do I have that B? I'm gonna have I read an empty
Because the only way that I would have an empty is if I didn't have a B right after. Like if I have more than 0 B's, then I need the transition to go to Q1. Because I'm not allowed to have like an epsilon transition, right? I can't just jump to Q1. Okay.
Set all of the strings that are A star B star without having a transition from Q0 to Q1 really.
Oh, I see. You mean no, I see. You're saying you would have something like A right goes to Q1? No, then that definitely doesn't work, right? Because if you just have the blank and you don't have this, right? Then how can you transition to Q1? But there's no. Yeah. Nice. Good question though. Yeah.
I did like from Q0 to QA directly, blank reads blank.
Q0 to yes. So okay, nice question. The question was, can I also add? Yeah. Okay, so I can see why you would want to do this. There's a bit of a problem, right? The problem is now you have a non-deterministic Turing machine, right? Because, but let me just say that you're not actually allowed to do something like this if you want to create a deterministic infinite tape Turing machine, because here you have non-determinism. Maybe that's not what you meant, but this is a good point to just clarify. Okay, yes. What did you actually mean? Sorry.
I didn't add the Q0 to Q1 the empty.
From Q0 to
I
Q1.
didn't add the empty.
Okay, what did you just had a different?
Yes, so like you see like below the B to B1, move to the right from Q0 to Q1, and then below it is the, if you read empty at Q0, you go to Q1. Instead, I have, if you read empty at Q0, you just go to the QA.
I'm struggling to see how that's different from what I just drew. Let me maybe talk to you after because I'm not really able to visualize it. Sorry. Okay. Any other extremely tough questions where I need to visualize a Turing machine in my head? Oh God. Yes.
It's not 12.
Okay.
What is the R mean? Sorry, I'm a little bit.
Oh, R is just right.
Like
move the pointer to the right.
oh, okay.
Move pointer right. And L would be move the pointer to the left. By one, right? One cell. Yeah.
And small follow-up.
Yeah.
If we read a blank from Q0 to Q1, why are we not allowed to then read these by the structure or
This means that we read a thing that is not in the language. Like you're not in
if you can do this.
and then what rule says we can't start suddenly reading these other than common sense that you just
No, because if the input string, because you sort of start, so if the input string, if at Q0 you're starting on a blank, that must mean that what you were given was empty. Because the convention is that the Turing machine starts at the leftmost part of the input string. So if that's the case and you're starting at a blank, and because blank is not a part of the input alphabet, then that means that what you got was the empty. Yeah. Does that make sense?
Yeah.
Okay. Nice. One last question, maybe.
Why is it that we don't accept infinite strings? Like,
why don't we accept infinite strings?
Yeah. Like,
for the purposes of all the automata we've seen until now, we only consider finite strings. Yeah. There's a whole different theory on how you would accept infinite strings. Yeah. Nice. Okay, cool. Let's move on to the next question. This one is maybe slightly more challenging. So it's going to be same type of question, except that now I want to create a Turing machine for A n B n, where just to simplify my life, this isn't actually in the question. In the question, it's n greater or equal to 0, but I want to avoid some edge case so that we don't waste our time on edge cases. I'm going to assume that n is at least 1. Okay. So let me give you a few minutes to think about this, because now in this case, we're actually going to, probably need to use the marking or the writing capabilities of the Turing machine, right? So my pointer is going to start at the leftmost part of the string, and I want to somehow design a Turing machine that checks that it has the same number of A's and B's. So I'll give you 2 minutes to think about it, and then we'll talk about it together. All right, what was it?
this. So Q0, if you read A, you keep looping. And then when you read the B, you
Right, but this doesn't work if, oh, I see.
and then I just have this.
Oh yeah, that also works. Yes. Okay, yes. All right. Sorry, time is okay. Well, but there's a timer. You can't hear it, but time is up. All right. Okay. So let's see. How are we going to do this? Well, let's first think of how I'm going to use the tape to do this. Essentially, this is like a common trick where you're going to sort of use the strategy of marking um, sort of letters for to indicate that you're sort of crossing them off one by one. It's kind of the general strategy. So what I'm going to do here is, for every A that I read here, I'm going to mark it with maybe an X. Once I mark this A with an X, I'm going to move right until I hit my first B that's unmarked. When I see my first unmarked B, I'll mark it with a Y. So, this has been crossed off with an X, this has been crossed off with a Y. Now I'll just repeat this, right? So I need to create a while loop in my Turing machine, because otherwise there's no way of doing this if I don't have a while loop. So then I'll loop back. Now what I'm doing is I'm looking for the next leftmost unmarked A. I don't actually know where it is, so I'm going to loop through the A's as well. At some point, I'm going to overshoot the leftmost unmarked A by 1. I'm going to hit an X. When I hit an X, that tells me that I went left by one too many. So I just have to move back right, and now I'm going to restart the loop, right? And that's how I create a kind of while loop with my Turing machine. So then again, I'll mark this A with an X. I'll mark this B with a Y. Now, at this point, I've marked everything. I need to define what the stopping condition is going to be. Well, the stopping condition is, my Turing machine is going to act as if it was looking for the next leftmost unmarked A. So it's going to move left. It's going to see this first X. It's going to tell itself, oh, that means I overshot by 1. So to the right must be another A. But to the Turing machine's surprise, when it goes right, it doesn't see an A. Instead, it sees a Y, which tells it that it should stop marking and it should just check that there's no extra B here, for instance, right? And because I was doing sort of a one-for-one marking thing, this tells me that I have the same number of A's as B's. So how am I going to do this with a state transition diagram? So because I'm assuming that I have n greater or equal to 1, I don't have to deal with the empty string edge case. So I know that I'm going to have at least one A, which I'm going to mark with an X and move right. Then at this point, I'm going to move through all my other A's. I'm going to move through all my other A's. And at some point, I'm going to hit a B, right? So the B that I hit, the first B that I hit, I'm going to mark with a Y. Now I'm going to move back left. As I move back left, I have to move through the A's, right? Because I'm looking for the first X. So I'm going to move left through the A's. And then at some point, I'm going to find my X, which is going to tell me that I've overshot the leftmost unmarked A by 1, and I have to restart, right? So once from here, I see an X, right? I'll move right, and I'll restart this loop. Now, the people who have seen this example maybe already might see that there's a few transitions missing. That's because, okay, I'm back here. So I mark this A. Let's mark this A with an X. Now I move right. Now I don't have A's to go through. I have Y's to go through. So that's okay. Let me just add that transition for moving through the Y's. Then at some point, I'm going to hit the unmarked B if I do have something that looks like A and Bn. This unmarked B is going to get overwritten by Y. I'm going to move left. Then, yes, I do need to move through my A's, but I also have to move through my Y's, right? So I'm also going to move through my Y's in between. Then, I'm going to do the same thing. I'm going to wait until I find this first X. I'm going to move right, but now I don't have an A. Instead, I have a Y. That tells me that I should sort of just check that I marked everything on the side of the B's, right? So let's do that. If instead I have a Y, I write a Y, then I go through all my Y's to the right. If I have a B here, right, if I have an extra dangling B here, I'll just jam and halt and reject, which is exactly what I need to do. So the only way that I go to QA is if from here I see a blank, right? So I see a blank, I don't touch it, I move right or left, doesn't matter, I get to accept, right? And so this is how you do A and Bn with a Turing machine. Right. Nice. Cool. Any questions about this? No questions. Nice. All right. So let's do a bit of a harder one. It's going to be question C, where we want to do same question, same deal, design a Turing machine, but now we want to do it for AN, B2N, C3N. Again, I'm going to help myself out a little bit, and I'm going to assume that N is greater or equal to 1. This isn't the case in the actual problem set question, so please make sure that you actually deal with edge cases if there are some that exist. Okay, so in this case, right, it's not something like ANBN or ANBNCN. It's something that actually is not context free, right? So I mean, in these two examples, these were a bit toy because I could have used an FA or a PDA respectively to accept them. In this case, I do actually need a Turing machine because this is not context free, right? Not context free. So a Turing machine is absolutely needed. Okay, so how is this going to work? Let me give you the general idea. So suppose I have the string A2, B4, C6. Okay, then it's going to be the same general idea of like marking. It's just that now for every A that I mark with X, I'm going to mark 2 B's with Y and 3 C's with Z. And I'm just going to loop, right? This is going to be my sort of a while loop that I'm going to design in my Turing machine, right? So I'm going to do that. Then I'm going to move my pointer left. Then I'm going to hit this X, tells me I overshot. I move right and I repeat, right? So that sort of allows me to close the loop that I've created for myself, right? So this A I mark with X. These 2 B's I mark with Y's. These 3 Z's I mark with Z. Then the stopping condition is I have an X. I move right instead of seeing a B, or sorry, instead of seeing an A, sorry, I see a Y, which tells me that I'm done marking any A's. So I'll just walk through my Y's and my Z's, ensuring that I have a blank at the end. Okay. Okay, so that's what I'm going to do in the state transition diagram. I wasn't planning on drawing it, but because we're slightly ahead of schedule, it doesn't hurt to do it. So let's see, I'm here at the start state. If I see an A, I overwrite it with an X. I'm going to loop through the remaining A's. Whoops, yeah. Loop through the remaining A's until I hit the first B, which I'm going to mark with a Y, and the second B. So this has to be hard-coded, of course. Well, not necessarily, of course, but now you know that it has to be hard-coded. Then I'm going to loop through the remaining B's. And then I'm going to get to the C's. So the C's, I'll mark one with a Z. Then I'll mark another one. Whoops. I'll mark another one with a Z. And then I'll mark one last one with a Z, but now I'm going to go left instead of right. And now at this point, I have to sort of loop back. So to loop back, I need to loop through the Z's, the B's, the Y's, and the A's. Right, so that's going to be here. I'm going to loop back. What did I just say? The Z's. Yes, thank you. But also the B's. Let's not forget the B's. And the A's. Yes, thank you very much. Okay. And now the way that I'm going to know that I have to reset is if I see an X. right? So if I see an X, then I'm going to have to reset, move right. And at that point, I'm going to restart. And what I usually like to do with Turing machine designs is I don't put all the transitions all at once. I just do a second iteration, and that tells me what transitions I've missed. So in this case, this has been so now I'm here, right? So then I'm here at this state, so I mark this with an X. Then I have to move through the A's, but also the Y's, right? So I have to add this. So I move through the A's and the Y's. Then I hit these B's, right, which I overwrite with Y's. Then I move through the remaining B's, but I also now have to also move through the Z's, which I just marked. So I move through those with right pointer moves. And then, I get to the C's, which I can mark with Z's, right? And then all of this is okay. So I'm looping all the way back here. Now, at this point, I can design the stopping condition, right? So I overshoot, I move left. I sort of am reading X. That tells the Turing machine, it thinks at least that it's overshot, so it moves right. And instead of seeing an A, it sees a Y, which tells it that it's done marking all the A's, and that it should just loop through the rest, checking that there's no like extra B here or extra C here, right? So that's what I'm going to do. I'm going to go through the Y's and the Z's. And if I see a blank, then I can move right or left, doesn't matter. I go to the accept state, right? And maybe just notice one thing. The reason why I'm marking each of these individual symbols with like different letters, right? So with Z's, Y's, and X's is kind of because of this sort of thing. Here, I need to sort of loop, I need to loop back through the Z's and the Y's here, right? So if I was using the same symbol, then I would sort of necessarily have to introduce non-determinism because I would have the same symbol for this and for this guy, right? So then your Turing machine has to make a non-deterministic guess, which because it's supposed to be deterministic, it can't do, right? So that's why you need different letters, different symbols. Nice. Okay, so there's another deterministic infinite tape Turing machine, singular. Any questions about this? Yes.
Why don't we have to split up the, oh wait, actually,
This case?
yeah, he just talked about.
No, I did not. No, that's a good question. I was expecting this question. The reason why here I can merge the case is because I've done the sort of order check in this loop, right? So now the only thing this is checking for is I don't have like a B that I'm not supposed to have or a C that I'm not supposed to have. Yeah, that's a good question.
Penalized for taking out low breaks?
No penalties for correct, understandable solutions. Nice. Yeah.
If I have actually no.
Okay. Okay, nice. Cool. All right. Let's do another one. So again, same type of question. In this case, we want to design a Turing machine that accepts the language W hash W, where W is in A, B star. Okay, let's keep the edge case of the empty string. And maybe one thing, so this hash symbol is just like a special tape symbol. So you can kind of assume that on your tape, you have something like A, B, B, and then the hash, and then A, B, B, right? So the hash is kind of there as kind of a helper so that you don't have to know where the middle is. There's another question in the problem set where you do have to actually determine that first. But for the purposes of this problem, we're not going to do that. Okay, so I think let me give you another 2 minutes to try it out. Um, yeah. Okay, it's also not going to ring again this time, but yeah, all right. How anticlimactic. You should never have a timer that doesn't actually ring. Okay, nice. So hopefully you had the time to at least think about it a little bit. Let's first think about how to do this at just like the tape level, right? So I have ABB hash ABB. How am I going to sort of try to recognize it? Again, almost always when you're doing sort of language recognition problems, you need to use some form of like marking, which I'm going to do again here. So essentially what I'm going to do is, if what I read here is an A, then let's mark this with, let's say, an X. Let me sort of loop through the rest of the string to the left of the hash. And then let me look for the first unmarked string on the right side of the hash. If it's an A, then I'm happy. I keep looping. If it's not, then I'll just halt, right? So here it is, right? And so I mark this with an X, and then I sort of resume. So then, I do this overshooting thing. I move right. Now I have a B, right? And the logic is very similar, but it's just that, maybe I'm going to mark it with, in this case, a Y. I think in this case, it actually doesn't matter if you're marking with the same or different letters, but let's just use different letters. But the thing is, though, here, if I mark this with a B, it's because if I'm marking this with a Y, it's because I'm reading a B. So then I have to look for the next unmarked letter to the right of the hash as a B. So that tells me that the logic for this case and this case is similar, but not exactly the same, which tells me that I should have like two branches in my Turing machine. So there's a branch for A and there's a branch for B. So that tells me that in general, like I'm going to have some loop here, right? But within this loop, there's going to be like two cases, right? So you can think of this as like two if statements. If I see an A, right, I'm going to mark it with an X. And then eventually I should see an A to the right and mark it with an X. If instead I see a B, then I'll mark it with a Y. And here instead I should, rather than seeing an A, I should see a B. Right. So that has to, like, that sort of almost by definition has to be in the construction of the Turing machine, right? Otherwise, I'm just going to confuse things. Okay, so let's try to see how we can do this. So I start here. So my start state is actually going to be the place where I'm going to branch. So if I have an A, then I'll mark it with an X and I'll move right. If instead I have a B, then I'll mark it with a Y and move right. I'm going to move through the rest of the string. So this is nice because it's kind of like a parallel thing for both branches. Then eventually I'll hit the hash. Right? Then in this top branch, what I need is to look for an A, right? So I'll look for an A. I'll mark it with an X, and I'll move left. Give me a moment. And then instead here for this branch, I have to read a B, mark it with a Y, and then move left. Then this state is going to be the state where I'm going to move back left. It's going to be the same logic for had I marked it with an X or a Y. So I'm going to have a single returning sort of self loop there where I need to, let's see. So I'm here, I have to transition through the let's see, do I need a different case for the, give me a moment, give me a moment. I see. So I need to first transition through the sort of first half of the string where I marked for X's and Y's. Then I'm going to see a hash eventually. So I'll move left. Then I'm going to sort of loop through the remaining A's and B's. And what tells me that I overshot is if I either see an X or a Y. Right? So if I see an X or a Y, then I return here. Right? So then now I do the second iteration, which is going to tell me which transitions I missed. So I move back right. Then in this case, I see a B. So I mark it here with a Y. I go through the remaining strings, A's and B's. Then there's the hash, so that's fine. Then here I have to go through the X's and the Y's. So that's the transition that's missing here. As well as here. Right. Then eventually for this branch, I should see a B, which I'll mark with a Y. And then I'll go through the X's and the Y's. Then I'll see the hash. Then I'll move through the A's and the B's. And then I'll see an X or a Y, which will allow me to go to the start state and restart. Now, the last thing that I need to do is the stopping condition. So when do I stop? I stop when I moved right, I saw a hash rather than A or B. Right? That tells me that I should stop. So if I see a hash, I move right. Then I go through the X's and the Y's. And then there shouldn't be like a dangling A or B here, right? So the only way that I can accept is if I have a blank, right? If I have a blank, then I go maybe right to my accept state, right? So this is, and just maybe the reason why I hesitated a little bit here is I was going to put all of these transitions in the single state here, but then you would have gotten non-determinism because of this transition. So that's why I had to separate. Yeah. Yeah.
Can I see the language again? Okay.
Yeah.
So the input string can contain some tape markers.
The input string can contain some tape marker. Yes.
But what if it already contains something?
Well, we're assuming that we're assuming that the input alphabet is AB.
Oh, okay.
Yeah. Okay. Nice. Yeah.
Can you explain what you mean by non-determinism in like the last branch option?
Maybe, so the question is about non-determinism and this thing, Right. So here, right at this point here, if I look at my tape, I may be here. I just marked the B with an X or the B with a Y, or the B with a Y, sorry. So then I have to loop through here, right? So if I have a Y, then I don't touch it, I move left. If I have an X, I don't touch it, I move left, right? What I was going to do is also, if I have the hash, then I write the hash, I move left. If I have an A, then so then I'm here. I have an A, then I don't touch it, I move left. If I have a B, I don't touch it, I move left. And then I only know that I overshot if I have a Y, right, or an X, right? But then, right, then I have a non-deterministic sort of transition specification because I have in this state a rule for X where I stay here and go left versus, and also a rule for when I have X, I sort of move right and I go back here. So it's like two things that I can do. So then you get non-determinism. Yeah. Yeah.
Can we use X for the model as market probability?
Yes, you can. Yes. I said yes. I feel like you want to ask a question. Yeah.
Like the stuff, but there's like all characters. Like
The input alphabet.
all characters. The hashtags.
If the
How do we do the market?
well, you always assume that you take the input alphabet and then you like add a prime to it or something. Like you always assume that, yeah, like you could do something like that. You could apply some letter operation to each of the elements in the input alphabet. Yeah. Yeah. Nice. Any other questions about this? Is it clear or is it okay? Nice. Alrighty. So let's move on to the last thing I want to talk about, which is, so now we've been talking about Turing machines as language acceptors, but we can also talk about Turing machines as implementers of functions. So in fact, if you have a function, the sort of formal way of showing that the function is computable is to argue that there's a Turing machine that computes it exactly, right? That's why this is sort of in general relevant. So suppose I have some function that takes some input string x and maps it to f of x, right? So the convention is the Turing machine will take the input string x. The pointer will start at the leftmost part of the input string and it'll start at q0. And what the Turing machine should do is that it should compute f of x, and that's the only thing that should be on the tape at the end, right? So f of x should be on the tape instead of x, and the pointer should be back at the left, but now at the leftmost part of the output, and it should be in the accept state, right? So the reason why we force this is because you can imagine you have several Turing machines like stacked together. And so then like if two Turing machines are supposed to compose functions, then this kind of works out because you're always sort of feeding into the next, right? Okay, nice. So this is the convention, right? Now let's see how we can apply it. So this is going to be question 2C from the problem set. Or actually, let's do the easier one first. Let's do D. So D is given some input string over the alphabet AB, the function should duplicate or copy the string. Right? So this is the copy function, right? Okay. So the reason why I'm doing this one first is because it's very similar to the previous Turing machine. Okay. So the way that this is going to work is, I have my blanks, and then at some point I have my input string. Maybe it's A, B, B. So, my pointer starts at the leftmost part of the string. You start at the state Q0. Then how am I going to sort of copy the function? Well, I'm going to sort of do the similar idea of like marking, but the important thing is, for every sort of, I'm going to have a branch where if I see an A, then I'm going to mark this with an X. Then I'm going to sort of loop through the stuff that hasn't been marked. When I get to the first blank, I have to sort of copy, right? So if I was reading an A, then this blank should be overwritten to an A. The thing is, because of like non-determinism, what I'm going to do is I'm going to overwrite it with a different letter for now. So I'm going to overwrite it with, let's say, capital A. Okay. And this is kind of necessary. I know it's necessary because I know what the state transition diagram looks like. It's not obvious when you're doing it here that you should use a different symbol. But when you do the state transition diagram, you're going to notice there's a non-deterministic thing. And then you're going to tell yourself, oh, then that means I should use a different symbol. Right. That's how I figured it out the first time. So otherwise, it's not at all obvious. Then you loop back, you overshoot, so you turn right, you move one to the right, you overwrite this B with a Y. Then again, you do the same thing, except that now you overwrite the blank with a B. Again, you do the same thing. This B becomes a Y, the blank becomes a B. Then the stopping condition is, you get here, you move right, and this is sort of the sort of determinism I was talking about. Here, right, I didn't want to like write an A because if I wrote an A, the stopping condition would have failed, and I would have gotten an infinite loop, right? So instead, here I see I have a capital A, so that means I should stop, and I should convert all of this to just letters. So maybe one way to do that is I move all the way to the right, and then I start moving left, where I'm like converting the capital B's, and then the Y's, and then so on, right? So that's going to be the general idea. Okay, so let's try to do that in an actual state transition diagram. So I'm at Q0. Let's see, if I read an A, then I'll overwrite it with an X, and I'll move right. I'll loop through my A's and my B's, and eventually I'm going to have capital A's and capital B's. And at some point, I'll get a blank, which because I'm in this branch, I'll mark with a capital A, and then I'll move left, and then I'll sort of move all the way back through the string. So I would need to loop through my capital A's, my capital B's, so the things that I sort of use to copy the string, and then through the unmarked A's and the unmarked B's. And then eventually, the stop, not the stopping, the sort of kind of looping condition, the way to close this loop is if I either, see an X or a Y, that tells me I overshot, so I should move to the right. So that's what I'm going to do. So if I see an X, I overshot, so I move right. If I see a Y, I overshot, so I move right. And it's going to be exactly the same sort of logic, which is kind of parallel for B's, right? So if I see a B, then I move right. The transitions, so they're just going to be transitions T. I'll just put T here. Otherwise, I'm not going to have the space. Then at some point, I'll see a blank. I'll overwrite it with a B, and I'll move left, right? And then, I'm going to loop back. I'm going to loop back through the B's and the A's. Again, I'm going to mark, in this case, so then I'll go back here, and I'm going to see this B. I'm going to overwrite it with a Y, move right, write a B instead of this blank, then loop back left. Then looping back left, I'm going to see a Y, so I'm going to move right. And now instead of seeing a lowercase a, I'm going to see an uppercase a. It could also be an uppercase b, in which case that tells me that I should just convert, right? I should end this thing. So if I see an A or a B, then I'll loop through this stuff. until I hit a blank. Once I hit a blank, right, then it's time to convert all of these uppercase things to lowercase. And the reason why in this case you couldn't have marked the A's and B's both with X's, because then you wouldn't have known what to reconvert them back to. So there's a reason why I used a capital B for B and a capital A for A. That's because now I know that, if I have a capital A, then I convert this to a lowercase a. Same deal for capital B. Same deal for X and Y, oopsies. And then eventually, I'm going to move all the way to this blank. And then once I see the blank, I'm going to move right? And then return. Okay, and so that ensures that, my pointer is back here, and now I have ABB, ABB, right? Which is exactly what I needed to do, right? Okay, nice. So there's another Turing machine for you. So many Turing machines today. Yeah.
You would have to make the input string and output string start like the same thing.
No, you don't have to make the input string and output string start at the same position, but there should be nothing to the left and to the right of the output string. Yeah. Yeah.
So for like
exam purposes, yes, very relevant.
I mean, just like the idea is that deterministic Turing machines are easy enough, so we're expected to do them and not like leverage non-determinism.
Yes.
Okay, which we had to do for context-free grammars because sometimes it's like not possible.
That's right. Yes. So here, because non-deterministic and deterministic Turing machines are equivalent in expressive power, we just make you do the deterministic one.
Okay.
Yeah. Yeah. Equivalent in expressive power when it comes to deciding languages, but maybe not when it comes to time. Right? It's very convenient to be able to guess things always correctly in an algorithm. Yes.
After from Q naught, why do you go the transition? Why do you have transitions to the bottom of it, like AAR and then DBR? Then you go to the end of the input string, the tape.
Yes.
And then you start writing the letters back. Why do you have to go?
Not sure.
You have the Q naught, right?
Because here I have to go through all of what is unmarked and also what's already been marked. And so I need to find the next blank.
Yeah, but the transition beneath Q0. Like when you're done
This?
processing the string.
Yes.
Yeah, you follow the arrow down. Yes.
Right. There's different ways of doing it. Like the way that I did it is I just move my pointer all the way to the right, and then I move it back left and I convert. You could also have converted here. Right? There's many ways of doing it. Yeah. Nice. All right. I think we have time for one more. So let's do the one that is maybe a bit trickier. So this is going to be C. So C is you're given essentially a natural number in unary. By the way, did we handle the edge case of the empty string? We did not. So let's just say this has to be greater or equal to 1. So that we, I leave the edge case for you. Okay, good. So you're given a natural number n in unary, and what you want to do is essentially want to do 3 times that natural number plus 1 in unary, right? So unary is like binary, except that you only have 1, right? Okay, that's why it's called that. Okay, so how does this kind of work? Again, just to avoid a repeat of the edge case, let's assume n is greater or equal to 1. So, suppose I have like 2, right? So n is equal to 2 here. What I should get is, 3n plus 1. So hopefully that's 7. Yes, I think it is. So this is Q0, right? And so what I should get at the end is I should get my machine pointing at QA to 7 ones in a row. Right? This is what I want. Okay? All right, so this one's a bit trickier. So I'll give you some time. How much? Maybe let me use a timer that makes a sound when it's done. If I have one, it's nice.
Does the pointer like does the pointer have to point at the start of the
Yeah,
before it?
like here.
Yes.
Yeah. And it has to be like there can't be like other stuff here. Like it has to be blanks. Yeah, it's kind of annoying, but it's convention. Hmm. Let's see. Let's see what we do. All right. So there's a few ways of doing it. Let me show you one. Do I have? Yeah, I won't have time to do the state transition diagram, but I'll post it. Don't worry about it. Let's see. The way that you can do this is, well, let's take this example. So the way that you can do this is essentially, again, using kind of the marking logic, where essentially for every one here, I maybe just mark it with an X, then I move right, and what I'm essentially going to do is I'm going to create kind of like a buffer zone for my like kind of scratch pad. So I'm going to have like this blank be my buffer. After this blank, after this first blank, for this first one that I read and marked with an X, I'm going to convert 3 blanks to X's, right? So I'm going to convert this first blank to an X, the second blank to an X, and this third blank to an X. And then I'm going to loop back through my X's, then the blank, then through the ones. Then I'm going to overshoot by reading an X. Then I'm going to go back, and then I just repeat, right? So then I'm going to read this one, convert it to an X, and then read sort of the remaining ones here, go through the blank, read through the X's, convert these 3 blanks to X's, right? Give me a second. Then I'm gonna move left. I'm gonna overshoot. I see that there's a blank, right? That tells me that I am done sort of repeating or triplicating, if that's a word, the ones for X's, right? So I've done the like sort of 3 times N, right? So that tells me that there's a few ways of doing this. I can loop through these X's, then I'll convert one last blank to an X. Then I'll go back, converting these guys to ones. Then at some point, I'm going to hit my blank. I have to erase all my scratch pad, all my work, right? So these, I'm going to go through these X's, convert them to blanks. Then I'm going to hit a blank, then I'm going to move right until I hit a 1. Once I hit a 1, yeah, this is kind of annoying, but I'm going to move left and then move back right, and then I'm done. Right? Because then I'm going to be pointing to 7 ones in a row. So this is one way of doing it. There's maybe another way where for every one that you read, you add 2 additional ones. Maybe that's more elegant. Yeah, I feel like it is maybe. So yeah, okay, let me just quickly talk about that other way before we, yeah, because this is kind of ugly. So what you could also do is I mark this one with an X and I mark 2 blanks with an X and I just do 2, right? But that's fine because I already have 1, 1 here. So then again, I mark this X, this one with an X, then I mark 2. Then I see that, so my stopping condition as I see a blank, I can convert this blank to an X, which is nice. So I get the +1 for free. Then I move right, and then I move back left, converting the X's to 1s. I hit the blank, I move right, and then I'm done. So that's another way. Yeah. Yes, yes. That's another thing. Yes, good point. You could also not have the buffer blank if you're doing something like X and then YY and then X and then YY. Yeah, is this the most elegant? Maybe this is also even nicer than this. So then you move, the stopping condition is now, oh, you see a Y. So then you move right, and then you see a blank, you convert that to maybe a 1, then you move left, and then, yeah. So that's another way of doing it. Yeah, nice. So that would also be nice. Cool. Any other possible solutions before we go? No, doesn't look like it. All right, so I'll post this. Have a great weekend and see you next week. We'll be talking about reductions and decidability and recognizability. Thanks very much.